Welcome everyone. In this video, we're going to pick up where we left off in the last lesson and open up that capture we took in PulseView of the UART transmission on the router. We're going to look at decoding that and then also take a look at some of the characteristics of UART transmission. So let's get started on that right now and open up PulseView. Okay, and we don't actually need to worry about connecting our device or anything this time because we're just going to be looking at that previous capture that we took. So in order to do so, we can just go here and click open. And then if you, from this drop down, just go all files. And then we're going to choose this TP-Link router UART boot up capture or whatever you saved it as from the last lesson, if you're using the one that you saved. And click open, and then perfect. We can see here we've got that same capture and we left off right where we were at. So if we just zoom in, and again, I'm using the scroll wheel here to zoom in, and you can use the mouse left button to drag and move it along. So we can see we've got all of this UART capture going on. I'm just scrolling through it right now. But to us, this isn't super useful to try and figure out what's going on by just looking at these raw captures right here like this. So what I'm going to do is I'm actually going to apply a decoder to it, and that's going to help us decode what's going on with the UART. So to do so, we can click this button right here, which is for decoders. And we already know it's UART communication, so I'm just going to search for a UART one. All right, so what I like to do is I'm just going to grab this and pull it up to the channel that we're working on, which is this D0 channel. And since we don't need the other ones, just to clear them out of the way, I'm going to quickly delete them. So you just right click and delete. You're just going to help clear up our view here a little bit more. All right, perfect. Now you see it saying here there are no channels assigned to this decoder. So we'll just click on it here. You can leave it, you can change color if you want, but I'm just going to leave it and call it UART. And we're going to choose the receive line. So we are receiving here, remember? So that's why we're going to choose the receive line, even though we are connected to the transmitter. We're the receiver. And I'm going to set that to D0 here. All right, and then you'll see we have all of these characteristics that we need to set. And I'm just going to leave it here as the defaults because right now our device is actually just using the defaults. And I would say honestly about 95% of the IoT devices that I come across that have UART enabled on them, they use these defaults as well. So good to remember. So that is the baud rate is at 115,200. Data bits are 8. Parity is none. Stop bits are 1. And then this bit order is least significant bit first. The only change I'm going to make here is this data format it's going to display it in hex, but I'm thinking that this transmission is actually probably going to be ASCII data. So if we want to see that ASCII data in plain readable letters, we can just choose here, ASCII, and that is all perfect. So we can just close this. Now if we pick a pulse here, and I'm just going to scroll out and see where we are in the actual message. All right, let's grab one of these ones. This is one of the very first ones here. And if we keep scrolling in, and I'm just going to go to the start of this message here. Right over here, maybe. We can actually start to see the text that's being sent out as part of that boot log. So right here, we're even already starting to get some banner grabbing here, flash manufacturer ID. And then we're starting to get some IDs and even, a warning message here that's coming in about this chip. Now, if you're curious, you can scroll through here and take a look at all the boot messages. Again, if we scroll out here, like there's a lot of data that's being sent at boot up, and you can read it all through this. But keep in mind, this isn't the best way to actually view this data, and generally that's not what we're going to use this logic analyzer and the decoder for. This is more just for us to get a sense of what is going on with that transmission, what the properties are, and if we can't get it working to communicate with it, then we can use this logic analyzer and the capture to debug that. On our router, it's pretty straightforward. The pins were already labeled for us, so we knew it was UART, we knew which pins were being used, and we're using all standard settings, so it's pretty easy for us to figure it out. but it's not always going to be like that. And to prevent you from, pulling out your hairs, just trying a bunch of different combinations when you're trying to connect to the router, sometimes it's easier to get a capture of the data and then just inspect it, and you can kind of figure out what's going on. Now, in order to figure out what's going on, you're probably going to need to understand what is actually going on beneath the hood here with the UART and this decoder. So that's what we're going to take a look at right now. So I'm just going to zoom back in on the start of this message right here. Maybe not this one because it's all equals. Perfect. So we'll take a look at this flash manufacturer message. And I'm just going to zoom in actually just on the very first part of it right here. Okay, so if I pull back up the UART properties here, the first one we'll talk about is the baud rate. And we've already chatted about this briefly when we were talking about that, imaginary serial protocol that we were coming up with, the really basic one. And what this is this is the speed of the transmission. And essentially this is the amount of symbols per second that we are going to be sending. And you'll remember both the receiver and the transmitter have to agree on that same speed so that we can decode the message. Now, if we didn't know what this baud rate was, and we tried some of the standard ones and we couldn't figure it out, we can calculate that. So the first thing in order to calculate it is we're going to actually have to take a look at the symbol width. And in order to do that, we need to find one of these pulses that represents just one symbol. So what you're going to look for is the smallest symbol that repeats itself. And I'm looking here, and in this transmission of data, I can see, these two here, but it's not super clear sticking out. So I'm just going to zoom out. And then, when I start looking more, I can see this kind of repeated. Here's one, here's one, here's one, here's one, here's one of this looks to be the lowest width pulse. So I'll just grab this one right here. And if you click up here on these markers, it's actually going to allow us to take a measurement. So what I'm going to do is I'm just going to drag it over this here. And we'll see here that it is 8 microseconds. And you'll recall that the way to calculate this baud rate is it's 1 over this time. And we don't have to use the calculator. The PulseView is going to do it for us. And it's measuring it as 125 kilohertz, essentially. Now, you'll notice this is off a little bit from the baud rate that we chose. And the reason for that is just going to be based on the sampling frequency that we chose. It's going to be slightly off. But the beauty of UART is we can actually be off by, plus or minus even 10% of that speed, and we're still going to be able to decode the message. So perfect. I'm going to clear these markers away just so it's a little bit easier to read. So that takes care of the baud rate. If we just go back to this F and zoom in on it, the rest of these UART characteristics that we have to set up, they all pertain to how we are actually going to be sending the data in each, what I'll say, kind of like portion of the transmission. So we already chatted about this a bit, but in networking, each, portion of data that we sent, we call that a packet. And that represents, a little bit of information, sometimes at the start and end in the header. And then it has the data in the middle. Well, in these lower end digital hardware communications, UART is not even a protocol in and of itself. We call each individual piece of data that we're sending like this a frame. So in this example right here, from here all the way over to here, this makes up what we call the frame. And then inside of that frame, we're going to have a few specific characteristics that help us to send that data and have it be decoded. So outside of the frame, though, is the first thing that I want to talk about, and that is this area right here. So you may have noticed when we started up the router that as soon as we powered it on, we saw the UART transmission line go to high. And we also saw that when we were probing it with the multimeter, that when it wasn't transmitting, it was just kind of in that idle time. Then it was actually just at that 3.3 volts constantly. And what this time is usually referred to when we're not transmitting is we actually call it the idle time. And the idle time will generally almost always hold that voltage on the transmission line at the high level. And there's a few reasons for this, but the main reason is that it allows us to fail off. And what that means is that if we have some sort of failure on our communication line, so our transmission line gets broken, whether that's a trace or something gets unplugged, or there's just an error with the transmitter itself, then we can detect that error because the receiver will see that UART line as low. Whereas if we just held our idle time as low, then we have no way to determine whether or not we're just not getting any transmissions because it's not sending anything or there's something broken. So you'll generally see that idle time at that high voltage. Now, in order for us to signal that we're actually starting the transmission, we need to have some agreed upon way to do that. And that's what's happening right here. You'll see we have the start bit. And the start bit in UART is always going to just be one low symbol. So in our case, it's bits, so it's just going to be one single zero or one single low pulse. And that indicates that we're going to then start transmitting the data after. So you see here afterwards, we have this binary here, and this is all of the pulses that make up the data. And usually this is going to be 8 bits, but we don't necessarily have to send 8. You saw in the UART decoder properties that we can actually change this to 6 or 7 bits, but usually you're going to see it as 8 bits because of course that makes up 1 byte. And then this 0 1 1 0 0 1 1 0, this is what then represents for us this F in the ASCII. So the next parameter that we need to agree on, and you may have seen this in the decoder there, is the stop bit. So if we take a look, that's actually right here. This is the stop bit, and it's kind of cut off here, but that's the stop bit. And the stop bit, just as the name kind of implies, this signals that this is the end of the frame, and we're going to then either go back to idle time, or we're going to, in this case, if we're just transmitting right after, we're going to send another start bit, and that's going to start another frame worth of data to be sent. So you'll always have at least one stop bit, but some devices will use more than one. You can use, potentially 2 or 3 stop bits. And the reason for that would just be if you maybe need some more time to allow for processing to take place or something like that. By default, it's almost always going to be 1, but this is changeable. So that's why you will be able to see it in those decoder options. So the last setting that we'll chat about, and it's not being used in this transmission, and with IoT devices, you're very rarely going to see it actually used, is the parity bit. And what parity does is we can actually perform some bitwise math on the data that's actually being sent. And then we choose our parity bit to be either even or odd. And what that means is that when we perform that bitwise math, if we use the parity bit, then it should make the operation of that bitwise math even or odd, depending on what we choose the parity bit to be. And if it isn't even or odd, then we know that we have some sort of error in our transmission. So it's kind of like a really, really basic way of doing a checksum for error checking. And you won't really very frequently see it used. So I just want to call attention to that. Usually you'll just see it left as none. So the last characteristic we'll chat about, and this is actually a funny one that we picked this F here now that I'm looking at it, is this least significant bit first is sent first. So the reason for F that's so interesting is that it's almost like a palindrome of itself, in that even backwards it's the same. But what that's essentially saying is that this hex number, if you're reading in its binary representation of this 011001110, this is the most significant bit here, and this is the least significant bit. This one, obviously, this represents the least amount if you were to convert this to hex. So this one is sent first, being the lowest one. So what I'm going to do is I'm just going to clear this writing off, actually, and we'll just take a look at a different one. And what I'm going to do is I'm just go back quickly back into the UART here, and I'm going to switch and I'm going to switch it from ASCII to actually look at the binary. So you'll notice the binary data here, it doesn't actually match up with these, what it's decoding it from. So here we have 00110, and then here we have 0110. And that's how it's showing that that least significant bit is being sent first. So it's kind of backwards, right? So here we have 0, that matches with this 0. Here we have 1, that matches with this 1. Here we have 1, that matches with this 1, this 0. and so on. So just something to keep in mind when you're looking at those bits. So if you keep in mind these different characteristics of UART transmission and you think you have a UART but you're not able to decode it, then what you can do is, without the decoder, we can zoom in and start looking at the bits and trying to frame it ourselves and figure out what's actually going on there, and maybe identify, for example, that we have a parity bit or something, or maybe realize that it's not actually UART that we're looking at and it's some other protocol or type of communication. With that being said, I'm going to wrap up the video here and I'll see you over in the next one.